In this next subsection, we'll look at Cartesian trees, which at first seem to have nothing to do with how we use blocking or how we use this sparse table solution on a smaller reduced instance, but it will solve the second part of that problem. And so I want to cover that first. This is about a very cute connection between the range-min problem and again a tree, but a different one, not the suffix tree that we had before. We've seen one connection. The range-min queries on the LCP array corresponded to lowest common ancestors of leaves in the suffix tree. We'll see there's another correspondence, and this is more direct and more convenient for us. So here's our array. In this section, I'll look at range maxima, not minima, just because then the drawing is more convenient. Of course, you can always take an array and negate all the numbers, and then you turn min into max, or you just flip the meaning of what less means. So this doesn't change the problem much. As long as you just want either min or max, the two are equivalent. What max means is we can draw the values of the array as heights of some poles, and then you get some nicer visualizations. So here I've done that. So again, the warning here, we'll look at max, just because it's convenient to draw. If I pick a range in my array, graphically speaking, what the range maximum is like having some pole covering this, a horizontal line covering that range, sink down slowly until it hits some tallest pole, and then it stops there. Right? So keep that picture in mind, some metal bar sinking down until it, well, it probably would tip over here, but let's pretend it's all sticky and there's super glue on top of the poles. So the RMQ on this slide means range max, and as always, it's the index, not really the value. Here's again the pole in nicer drawing. The task remains the same as before. You're given the array, and then we want to do fast at query time. Now, okay, I should have put this on Slido. Who has heard of trees? It's a portmanteau of tree and heap. You've seen binary search trees, you've seen heaps, but you may not have seen the treep. If not, doesn't matter much. It just turns out to be exactly that idea in disguise. So if you have seen it, you may say, oh, cool, I recognize that. If not, it's kind of irrelevant to this module. It's just a neat connection. The Cartesian tree is a binary tree on this array defined as follows. We take such a bar covering the entire array, let it sink down. It will hit the highest pole. Let's pretend here that the poles all have different heights. So if we need, we can make the ones with equal height. The leftmost is a tiny tad higher for our graphics. So here I picked numbers where at least the maxima in each range is unique, but there's obviously two of the same height here. Maybe it would have been better to put them at all different numbers. The Cartesian tree starts growing as follows. You have this pole covering the entire range sink down. Then it hits the tallest pole, say that's unique. And that becomes the root of the Cartesian tree. And now we split our metal rod at this position and let it sink down on the left and on the right independently. So this will sink down here, this will sink down here. We'll see that the next thing that this hits on the left is this one, and on the right is this one. These are the tallest poles outside of the globally tallest one. And these will become the next two nodes in the Cartesian tree. So that the global maximum divides the array in a left and in a right half, and then we'll build a Cartesian tree recursively on these two segments. And their roots will become the children of the global root. That's what we did here. The global root is the global maximum is the overall root. And from the left half, this was the tallest, so this becomes the next root. And here on the right, there's just a single node. If we keep doing like this, so again, here we hit the line, so we split it, we let it sync on the left and on the right independently until we find the next tallest pole there. We keep growing like this, and we get a binary tree. Because we always split into a left and a right half, every node will have at most two children. It can have no child on one side if it's right next to the maximum or on the boundaries. And we have leaves when things are a local minimum. Okay, nice construction. Why would we care about this tree? It turns out that the range max queries, pardon me, the range max queries are encoded in this tree. And the way they are encoded is if you have this range, you find the nodes that have the in-order position of the outermost points. So this range goes from position 6 to 14. I've labeled all the vertices in the tree using their in-order numbers. So in-order, again, is the traversal of the tree. You start at the root. You first visit the left subtree. When you come back, you take the next free number and stick that on yourself, and then you recurse on the right. So if we do that here, recurse, 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 we stick the 0 on the leftmost node. We come back. Next free number is 1. Stick that on that vertex. And then we continue in the right subtree. Next free number is stick there because it doesn't have left subtree. The way I always draw the binary search trees in Unit 2 and so on, this is just a left to right sweep of the vertices. So that's easy to do in this visual representation. But I want to stress that the information is contained in the tree. You don't need this nice layout. You can reconstruct it from just the tree. So you find the two vertices corresponding to the endpoints of the range, and then their lowest common ancestor is the range maximum. Okay. And in a way, the reason why that is the case, if you walk up from this vertex, you eventually have to reach the root. And whenever you walk up, you go to a position with a higher number, a taller pole. At some point, we have to end up in the root. So the paths join eventually, always. And the last time they are separated, that's the highest node in this pole, because if there was another one, the two would be separated. So I don't know, do we have a nice example for that situation? Yeah, it's just in the nature of the problem. When the paths, the lowest common ancestor is always a node where the two paths go, one goes left and one goes right. And so these two paths then from there on have to go jointly to the root, so they can't visit this range again. So we've translated the problem for finding range maxima or range minima to something on a tree. Now, it turned out again to be lowest common ancestor, but it's on a different tree. It's not a suffix tree. It's the Cartesian tree of the array. No strings involved, no strings attached, just the definition from the array. And of course, this works even if I take the array away. All I need is the tree, and I don't have to draw it in this particular way with nodes at the heights of the pole. All the information is just contained in the topology of the tree. What are the left and right children of each node? So you can reconstruct the in-order labeling, you can find the two vertices that correspond to the range endpoints, and you can find their lowest common ancestor. And that node's in-order index is the answer to range max. All you need is contained in the tree. That's the point of the Cartesian tree. All right, so see if that could follow that part. It's restarting. So here's a little example where you just are given the tree, and you're asked to work out what the range maximum is. As soon as Slider lets me log in again, I can start the question. Keeps redirecting to the login page. I don't know what the problem's. All right, finally. Okay, I'll switch back to the tree, even though you had like 5 minutes to study that in detail. Okay. And remember, we start with 0, so 1 is second from the left. I have 9 people so far. We've had 10. We had 22 earlier, but 15 for the example, so I don't know. Shall we try to aim at 15 again? 15 people or end of my patience, whatever comes first. Okay, let me show the answers. Various votes for 2, but also 3, and so on. So let me go through this slowly. First of all, we have to reconstruct the in-order indices. So we start at the root. The current next free number is 0, but we first visit the left subtree. Same thing, 0 is the next number, but we have a left subtree to go to first. And again, in this node, we don't have a left subtree, so we return, and still 0 is the next number, which we stick into this node. That's labeled 0. And then we visit its right subtree, but that's empty. So I return and go back to the parent. The next free number now, I return from my left child, now is my turn. So I put the 1 in this node and continue with the right subtree. Here again, left is empty, so I'm labeling this node now. Next free is 2. And then the right subtree is empty, so again, I go up. Now I have covered the left subtree of this node, and now it's this guy's turn. So the next free number is 3, and so on. If you do this for this tree, you see that it's nicely left to right because I was kind enough to align the tree that way again. Then we can find the 2 nodes that correspond to the range endpoints. These are nodes 1. Let me do that way. Nodes 1 and 5. And range min now corresponds to the lowest common ancestor. So we walk up the tree from there until we hit the root, and the point where these paths meet, that's the lowest common ancestor. And so the return value for RMQ is the index of that node, which is 3. A way to show the same thing closer to what we've had on the previous slide is to reveal what the array was that this comes from, even though it's not necessarily needed. And then here I've done the same thing. So that's how it connects to these bars. In a way, whenever you're given such a tree, you can invent an array that produces this tree, and you can work from there. But there are many different options to choose the heights of the poles. Here's one. I've generated a few larger examples just to see what these look like. So here is the array in very small print. And then you see the largest, the maximum in the entire array is somewhere here. So that gives a vertical dividing line to left and right. And that's the bar sinking down. So that becomes the root. And then we independently treat the left and the right and so on. So if you want to practice the construction, you can take that bigger example. And then you can draw the tree by compressing it, basically pushing it together. You can push the left and the right half, the right subtrees independently together. So it's the same tree, the same correspondence between nodes and their children, but drawn to use a little less space. And of course, you don't need these lines. You can just draw the tree. One little bit, and then you deserve your break. What we'll need is not just this correspondence. Range min queries are lowest common ancestors in the Cartesian tree. One key point why this is so helpful is that we've removed the array entirely. There are no values anymore. It's just one tree. And so while there are many, many different arrays with all the different values you could put in, there's a much smaller number of binary trees. We've seen, I tried to convince you by example, if you're given the Cartesian tree of an array, all the range min queries are answered, or the information is all there. Because for every pair of nodes in that tree, there's the lowest common ancestor is well defined, and that's the range min. So the question of how many different things can happen with range min queries if you're given an array is the same as asking how many different Cartesian trees are there. And every binary tree is possible as a Cartesian tree. That's what I said earlier. If you're given a tree, you can generate an array that produces that. And so you can just use look up the number of binary trees on n nodes is a known thing. It's counted by the Catalan numbers, which are well known in combinatorics. They're counting all sorts of objects that have intimate relations to trees if you look at it from the right perspective. But the formula is a bit unwieldy. What we'll use is just a simple upper bound for that, namely that the number of trees of n nodes is at most 2 to the 2 times n. And I want to prove that quickly because it's very nice and a constructive proof. What we'll have to do for that is construct a binary encoding of a binary tree. So that if the tree has n nodes, the binary code uses 2n bits. And why is that the case? Well, the number of such, the code should be unambiguous. You have to be able to decode the tree again from this code. So there's at most as many trees as there are binary strings of that length. And the number of those binary strings is 2 to the 2n. How can we do this? Well, you can, for example, for each vertex, you can have 2 bits which tell you whether or not it has a left child and a right child. So every node has potentially a left child and a right child, and you store a 1 if it has a left child and 0 otherwise, and you store a 1 if it has a right child and 0 otherwise. So we do a pre-order traversal of the tree. And we store 2 bits. Has a left child and whether it has a right child. So let's do an example with you. If Slido works again. So here's a little binary tree. And you're supposed to do the encoding I just described. So I should maybe Copy that over. That didn't work. All right. And we can just concatenate that for all nodes. We may reach the point where I'm losing you, so let me do it on this tree first. So what is a pre-order traversal? It's similar to the in-order traversal we had before, but now you visit the root first, and then you go left and right subtree. So in a pre-order traversal means you walk around the outer side of the tree like this. And whenever you see a node for the first time, you output its values. So you visit this one first, then this, then this, then this, then this, then this, then this, then this. And if we output the bits for these nodes in that order, the first one has both children, so it gets a 1, 1. The second has both children, so it gets 1, 1. This one has both children, 1, 1. 3 is a leaf, so it doesn't have any children. That's a 0, 0. Then we jump to node 4, which is also a leaf, 0, 0. And we jump to node 5. That has no left child, but it does have a right child, so it's 0, 1. And then node 6 again is a leaf. And we jump to node 7, which is another leaf. So from this bit string, you don't necessarily see anymore that this was a tree, but you can reconstruct it. You start reading the first 2 bits, which means you get a node. And because they're both ones, you know there's something coming here. And then again, you follow the next thing that you're looking at is this node. So you decode the next 2 bit. I have a node and it has 2 children. So again, I'm following down here. Decode one more, another with 2 children. All right. And so you always know which node you're decoding next, and you know whether it has the children or not. So you can reconstruct the tree that way. Let's revisit this question. I don't want to drag it into longer than necessary. So let me just show your answers. The pre-order traversal starts with this node, then moves left. This is the first time we hit this. We walk around the outside of the tree. So we have to encode it in this order. And then by the same means as before, this one has both. So it gets a 0, 1, 1. This one has only a left child, so it gets a 1, 0. And then the remaining 2 are leaves, so they get 2 zeros each. All right. I think it's a kind of a nice little addition to our compression unit, even though we didn't need it there. But you can represent the shape of a tree with 2n bits. It's relatively easy to encode and decode. All we need this for here is really to get this statement. The number of binary trees on n nodes is at most 2 to the 2n.